Okay, ready to dive into something a bit wild. Imagine like a logic puzzle. You know the rules. You can move the symbols around, but those symbols are totally meaningless. They don't stand for anything in the real world. Is that even logic?
Yeah, it's a really fundamental question that's kind of been bugging logicians forever, and it gets right at the heart of what we're looking at today, which is SMT, satisfiability modulo theories.
SMT. So this is like crazy powerful stuff, right?
Yeah.
Used for like verifying software, making sure things don't break. But the first time I bumped into it, honestly, it sounded kind of outrageous, like logic that doesn't care about meaning. How does that even
Well,
work?
that's the thing, right? SMT, you can almost see it as like a black box. You've got all these complex rules inside for how you manipulate the symbols, but it's not about what they represent out in the world. It's all about, can you find any solution that makes the rules happy, whatever that solution might mean?
So it's like superpowered Sudoku solver or something. It can fill the grid perfectly, but it doesn't care if the numbers are planets, pizza toppings, or just like nothing at all.
Exactly. That's it. And that's what makes it so powerful, but also so philosophically weird. Like, can you even call something logical if it's got no inherent meaning?
Our guide for this deep dive is this paper. It's actually a draft from 2021, Notes on Semantics of and Proofs for SMT by Chad E. Brown. Gives us a peek into this world where logic and meaning, well, they seem to go their separate ways.
Yeah, and the paper starts off by setting the scene, like traditional logic where meaning or semantics are just baked in. So think of like classical first-order logic, the kind you'd use for math proofs. Statements like 2 plus 2 equals 4. Those have clear meaning in the world of numbers.
Right, right. The symbols, two, the plus, the equals, they stand for things, relationships that we all agree on. And that shared understanding is what lets us do the whole logic thing, proving theorems, all that.
Exactly. Another example is Church's simple type theory, which underlies certain programming languages. Again, there's always this idea of what makes a statement true or false within a system, a kind of world, if you will.
So meaning it's foundational, right? In these logics we're used to. But then SMT comes along and it's like, hold my beer.
It really does. It says, what if we just ditch all those assumptions about meaning and we just play by the rules?
Okay, but in practice, how does a meaningless logic even work? How do you prove anything if you don't know what the symbols are supposed to represent? That's where I get kind of lost.
Well, the paper dives into two really interesting ways that you can prove SMT results, even without the traditional semantics. The first one uses this thing called CIC, the calculus of inductive constructions.
CIC. Yeah, that sounds pretty intense.
It's super powerful, but think of it this way. Imagine like a language so rich it can describe almost any math concept you can think of and then check if it's true. That's CIC. So you translate your SMT problem into this super language and then you use its powerful proof system.
So we're taking this meaningless SMT stuff and giving it meaning in a different, more powerful system. Isn't that roundabout?
It can be. That's one of the challenges. That translation can get super complex, especially as your SMT problems get more complicated.
Okay, so putting complexity aside for a second, can you really prove things about a system that doesn't inherently have meaning? I'm still kind of wrestling with that idea. What's the other approach the paper talks about?
That one takes us back to the basics, the world of set theory, which might seem kind of funny given how abstract and potentially meaningless SMT can be. So set theory, it might seem like old school math, right? But there are these really elegant ways to actually use it for proofs in SMT. The trick is we can axiomatize set theory within higher order logic, and that gives us these things called proof terms.
Proof terms. Okay, got to break that down a bit. What are we talking about here?
Think of them like super detailed receipts for every logical step you take. Like if you were a detective and you had to document every single piece of evidence to make your case rock solid.
Ah, okay, so it's like showing your work in math class, but
Yeah.
taken to like the extreme. So even though the symbols in SMT might not have like a concrete meaning, these proof terms let you rigorously show that the results are legit.
Exactly. That's it. It's a way to ground these operations in a system where you can really trace every step and be sure it's correct.
Okay. I'm starting to see how these proof methods, the CIC and this set theory thing, can work with SMT, but it's still kind of mind-blowing to think about proving stuff without inherent meaning. Does the paper give any examples to see this in action?
It does. Some really fascinating ones that show both the power and the strangeness of SMT. So let's start with induction. Imagine trying to prove something's true for all numbers, but you're not even defining what numbers are in the usual sense.
Wait, how do you even do that? Seems like you got to know what you're talking about before you can prove anything about it.
That's the wild part. SMT, it can. It works with these abstract concepts, relationships, without needing concrete definitions. The paper walks through this scenario where, even without a specific definition of number, SMT can still use induction to establish truth.
Okay, so it's like saying we don't need to know what these things are exactly, but we can still figure out how they behave based on the rules they follow.
Precisely. And that's super useful for something like software verification, right? You need to make sure your program works in tons of different scenarios, but you can't possibly know all those specifics in advance.
Right, right. Users could be inputting all kinds of crazy data, and the program's got to handle it.
Exactly. SMT lets you reason about the program's behavior in a more abstract way. You're not limited to testing specific inputs, but verifying it follows the rules correctly under all sorts of potential conditions.
So SMT's like meaninglessness actually becomes a superpower in this case.
Yeah.
It's a logic that's super flexible and adaptable.
Exactly. Now, ready for another mind bender?
Hit me. I'm starting to get a taste for this outrageous logic.
All right, so let's talk about the pigeonhole principle. Ever heard of that one?
Vaguely. Something about pigeons and holes, right?
That's it. It's this simple but powerful idea. If you have more pigeons than pigeonholes, at least one hole has got to have more than one pigeon. Now, get this. SMT can prove this principle without knowing what pigeons or holes are.
Seriously. It can prove something about pigeons and holes without knowing what they are. That's nuts. How is that even possible?
Because it doesn't need to understand those specific objects, it just needs to understand the relationships, the rules of the game.
So it's like SMT is saying, look, I don't care if you're talking about pigeons, socks, or like made-up math things. Give me the rules for how they relate, and I can figure stuff out.
Exactly, and that's what makes it so powerful for all sorts of problems.
This is getting weirder and more awesome by the minute. What other examples we got in the paper?
Well, this next one really gets at what can happen when you have a logic without traditional meaning. It's the Schroeder-Bernstein theorem.
Okay, don't think I know that one. What's the deal with it?
It's this theorem that's totally true in normal math, but can actually break down in the world of SMT. And this breakdown shows us what can happen when you're working with logic detached from the usual meaning.
A math truth breaking down in SMT. That's kind of freaky. Does that mean math is broken, or is SMT like its own weird math universe?
Those are great questions. It has to do with how SMT handles arrays, which are like lists of things. Schroeder-Bernstein is about whether two sets have a projection given certain conditions. The paper shows how with arrays, this can actually fail in SMT.
So something that's like provably true in regular math doesn't hold up in SMT. Whoa. It really is like a different math universe where the rules are kind of tweaked.
Exactly. And that shows both the power and the strangeness of it. It can achieve amazing things, but also give you results that make you rethink what you thought you knew about logic and math.
Okay, I need a minute to process all this. We've got this logic that doesn't care about meaning, these two wild ways to prove things in it, and now examples where math truths can break down. SMT is impressive, but also kind of scary.
It's a lot to take in for sure. But hold on, there's another big thing about SMT we got to talk about. Completeness.
Completeness. Uh-oh, I have a feeling this is going to be another wild ride.
Yeah, you're not wrong. Completeness in a logic system means that if something's true, you can prove it. Traditional higher order logic gets kind of tricky with completeness, especially when you start talking about standard models.
Standard models, what are those again?
Basically, it's an interpretation of the logic that everyone agrees on. It's like saying, okay, this is what these symbols and concepts really mean. But in higher order logic, it gets harder to even say what a standard model is.
So like in the real world, we all agree what a set is, but in these fancy logics, it gets more fuzzy.
Exactly. But here's the thing. SMT kind of sidesteps this whole issue. If there's no model that satisfies the rules, that often means there's a proof of unsatisfiability.
So like if we can't find any way to make this thing work, then we can definitely prove it can't work.
You got it. And this brings us back to that question we started with. Is SMT really logic if it has no semantics?
Right? We've seen how it works, how to prove stuff in it, even how it can mess with math truths. But is it truly logic without meaning?
That's the big one. And the paper doesn't give a clear-cut answer, which I think is good. It means we're dealing with something really deep, makes us rethink the foundations of logic and reason.
It's definitely made me question what I thought logic was. But we're not done yet, right? There's more to uncover in this world of SMT. So we've really gone deep here into this SMT world. Logic without meaning, these crazy proof methods, even math truths kind of breaking down. Powerful stuff, strange stuff, makes you wonder, What even is logic, right?
Hmm.
But is this all just theoretical, or is this meaningless logic actually useful in the real world?
That's a great question. And one of the most exciting things about this whole area, SMT, it's not just some abstract math thing. People are using it right now to solve actual problems all over the place.
Okay, yeah, let's get into that. We touched on software verification before, but where else is this meaningless logic showing up and being helpful?
One of the big ones is hardware design. So imagine you're building a complex microchip, right? You need to make sure all those parts work together perfectly, no conflicts, no errors.
Sounds like a job for SMT. You need to check the design without knowing exactly what data the chip's going to process out in the real world. That whole idea of general behavior, not specific details. Right.
Exactly. SMT lets hardware designers do that. They can use these SMT solvers to catch errors in their designs, make sure the chip will work correctly no matter what conditions it faces.
So SMT is helping make our computers, our phones, all our gadgets more reliable, less likely to crash.
Absolutely. And it's not just about reliability. SMT is also used to optimize hardware designs, making them faster, more efficient, using less power.
Okay, that's impressive. So beyond hardware, what else is out there?
Well, SMT is making big waves in AI too, especially for building AI systems that need to reason about things that are complex, uncertain, even contradictory.
So AI that's a bit more like us humans, we got to make
Mhm.
decisions with incomplete info all the time.
Good way to put it. SMT gives you this framework for building that kind of AI. For example, they're using it in self-driving cars, which have to make super fast decisions based on tons of sensor data all the time.
Wow, so this meaningless logic is part of some seriously cutting-edge tech.
It really is.
Yeah.
And it doesn't stop there. SMT's popping up in cybersecurity, finding and stopping attacks, and in bioinformatics, helping scientists analyze complex biological data.
So this tech, it could end up affecting almost every part of our lives.
I think that's fair to say, yeah. We're just at the beginning of what SMT can do, honestly.
That's exciting, but it also makes me wonder, are there any downsides? Limitations? If we're going to trust this stuff for self-driving cars, cybersecurity, that kind of thing, we got to be sure it's solid, right?
Excellent point. And yeah, researchers are looking into that all the time. One concern is that as these SMT solvers get more and more powerful, they could also become harder to understand, harder to control.
Like with any powerful tool, right? You got to be careful how you use it.
For sure. We need to really understand what SMT solvers can and can't do, not just blindly trust the results they give us.
Makes sense. Anything else to watch out for?
Well, one inherent thing about SMT is that it often deals with problems that are undecidable, meaning there are some questions that SMT solvers will never be able to answer with certainty, no matter how smart they get.
So even SMT has its limits.
It does. Knowing those limits is super important, helps us use it the right way and understand what the results really mean.
Good reminder that even in the world of logic, there are some truths that might always stay hidden from us.
Humbling, isn't it? But that shouldn't stop us from exploring, pushing the boundaries of what's possible.
So what's next for SMT? What are the big mysteries, the exciting things researchers are working on?
Well, one big area is making even better SMT solvers. Faster, more powerful, able to handle more complex stuff. The algorithms, the techniques, that's all constantly evolving.
Which opens up more possibilities for using SMT everywhere.
Right. Exactly. Another cool thing is developing new theories, new extensions to SMT itself. It's not just one thing, it's like a whole family of logics and techniques, always growing.
So they're making the SMT toolbox bigger and better, more versatile all the time.
Yep. And that's leading to awesome new applications in robotics, machine learning, even theoretical physics.
Amazing to think that this meaningless logic, which started as a pretty niche thing, is now making such a huge impact.
It really shows you the power of abstract thinking, how theoretical stuff can lead to real breakthroughs in unexpected ways.
I think it's safe to say this deep dive into SMT has been mind-opening. Surprising ideas, mind-bending examples, and a glimpse into a future where logic without meaning could really change the world.
It's been quite a journey. Hopefully it sparks some curiosity in our listeners.
Because as we've seen, logic is full of surprises. Who knows what amazing discoveries and uses are still out there waiting for us?
The possibilities are wide open.
And on that note, that's a wrap for our deep dive into SMT. Huge thanks to our expert for taking us through all this.
Happy to be here.
And to our listeners, thanks for joining us. Keep exploring, keep questioning, keep diving deep into the world around you. Until next time, stay curious.